bridge engineer for David Evans and Associates. He's going to be presenting on strengthening of a PT box girder bridge, extending the life.
I should mention that this presentation was done originally when I still worked at the Oregon DOT. Last January, I went ahead and switched over to the private side, working for David Evans and Associates. So when this project was done, I was the major bridge maintenance engineer for Oregon. We'll run through some background on this, the load rating, strengthening alternatives, what is near surface mount titanium strengthening, some construction, and most importantly, some lessons learned. I would take just a real quick segue and explain why is strengthening being covered during a bridge preservation partnership. If you look at FHWA's definition, it's not included, right? But as a bridge owner, I think it's a very important tool in the toolbox for keeping good bridges in service. And that was the case of this McKercher bridge. It was a fantastic bridge. Maintenance crews never had to do anything to this bridge, except we did an epoxy overlay at one point to preserve the deck. It just wasn't on our radar. It wasn't something that we had to do. Then one day the load rater showed up and slapped something down on the table and said, hey, this bridge doesn't rate out. And I'll get into the details of that. But right, it was not a preservation issue, but if we had not strengthened the bridge, it would have been slated for replacement. And honestly, in Oregon, we have enough bridges that are just in poor condition that we really like to see the funds go to replace those as opposed to these nice bridges. That's my kind of link into why does strengthening make sense for preservation. So here's the bridge. It was constructed in 1957. It's a post-tension box girder. Little side view, you missed the picture there. McKercher Bridge, constructed in 1957. As I mentioned, it is one of the oldest post-tension box girder bridges in Oregon. I think there was one that was built right before that, but it was definitely on that cutting edge of its era. It's a 124-foot main span, and those 25-foot end spans are cantilevers. It's just a 3-cell box, kind of a typical box girder kind of construction. One thing to note, it's only 4 feet deep, so it's fairly shallow for bridges of this span length. A 26-foot roadway. The shear reinforcement. This is what really made us struggle with this bridge, specifically from the load rating standpoint. Number 3s, right? Number 3 stirrups. You never see number 3s on a bridge anywhere now. But that was what we had. Number 3 stirrups, double legs. You figure number 3s, they got them pretty tight, right? They're nice tight spacing. No. 12 inches was the best we had, and then it quickly jumped to 24 inches. So not much shear reinforcement in this thing. And it's only grade 40 because of the era it was. So you don't have a lot of steel for that. It was really relying a lot on the post-tensioning and the concrete contribution back then. We rate bridges based on current design requirements. ODOT, they do the whole width approach that's allowed per AASHTO, LRFD, beamline analysis in MIDAS, and then ODOT has some internal tools to calculate capacity and rating factors in an Excel spreadsheet tool. And so this is what the rating factors came back with, right? So you have a bridge that's been in service for 60, 70 years, perfect condition, but the rating factors say close it or we're heavily restricted to all legal vehicles, take all the permits off of it, and emergency services are also no longer allowed, right? So this is something that I'm trying to highlight with preservation and strengthening being related. You know, this bridge would be slated for replacement if we were just to leave it the way it is, right? That would be completely unacceptable, even for a relatively low volume route. It's just kind of showing where some of those sections are. You got your critical shear section there closest to that first pier. Notice that the Strand Profile, that PT profile, that's that parabola going up and above, it's really flat right there. You're not getting much help out of the post-tensioning at that location. And as you work your way out, you finally get to that 18th point, the bridge, where you're still in that nice 12-inch stirrup spacing and the strand starts coming down. You actually got rating factors greater than 1 right there. So we were okay right at that section. And then as soon as you continue on, you go to the 24-inch stirrup spacings and the rating factors drop back down for shear. Just kind of showing how that post-tensioning profile really can make an impact. These are some of the calculations that were on it. You know, the existing shear capacity, whole width, was about 700 kips, and we needed about an additional 500. So it wasn't like a minor strengthening. We needed a lot of additional capacity to get the numbers to pencil on this bridge. Jumping into strength alternatives, I will just do a quick segue. We did try and refine the load rating on it. We looked at doing a grillage analysis on it. We looked at diving deeper into the capacity calculations, tried really, really hard to not do harm on this bridge, right? Like I said, it's in good condition. Last thing I wanted to do was go punch a bunch of holes in it, but it just would not get there. We ended up kind of contributing it to the fact that post-tension box girder bridges, at least I believe, have a lot more shear capacity than what they get credit for in the modified compression field theory. Strengthening alternatives, right? We accepted this bridge must be strengthened to stay in service. You got a whole list of options here within the bridge design manual. That's kind of ODOT's standard process. And so I started running through the list, right? Okay, I could widen the girders. Kind of difficult, but it's possible. You could do some additional post-tensioning, internal shear anchors, and then of course FRP are some other commonly used and viable alternatives. Say, all right, let's go field scope it. Let's go out there. This is your access up into the box. You got a couple manholes to get up to just the exterior cells. There is no access currently to the interior cell, so you'd have to cut a hole to get into it. Okay, we can still work with that. And you get into the box, and it's awful in there, right? Again, the whole box was only 4 feet tall. You got a couple feet worth of stem work. Like, you only have a little over 2 feet of room inside the box, right? So it's crawling. They left a little bit of the deck formwork in there that was falling off. Diaphragms that have pretty small access points through it. And so, we're looking at delivering this work in-house, working with our maintenance crew. That's them crawling in front of me. I'm taking the picture, just trying to remind myself when I go back to my desk of how awful it's going to be for them when they get inside this box to work on it. But they were up for the task. So we started looking at it. Widening the girders. Right? It's a very common approach to increasing either shear or flexural capacity. The concern is with all the dowels, right? Typically you would roughen the surface and then dowel in all that shear steel to get that interface shear capacity up. And I don't know where all those post-tensioning ducts are, but I know that there's a lot in there. And so I had concerns with the constructability of this repair. Near surface mount FRP. The primary concern with this is just the very, very short bond length, right? The boxes are only 4 feet tall. And then a vertical surface of the webs there, I have less than 2 feet. And so getting the bond for the near surface mount FRP would be a challenge. Defined workspace, and then I just really needed a big jump in capacity that I wasn't quite sure that FRP, well, actually ODOT wouldn't allow FRP in this situation because of the large increase in capacity. Internal shear dowels, this is very common strengthening in Oregon. It actually works really slick. Drill, roto-hammer a hole either from above or below into the center of the stem, miss your flexural steel and install that. But I got post-tensioning ducts, so that wouldn't work either. So I had run through the list of options to strengthen this bridge, and I came out with, I didn't have one. Fortunately, Dr. Chris Higgins from Oregon State University was working on the development of this near surface mount titanium bars, and we said, well, maybe this will work. At the time of this project, the guide had not been adopted yet by AASHTO, although it is now. And I think some of that will be covered in the next presentation by Dr. Higgins. It was another tool in the toolbox. So I had the guide spec from kind of like the bootleg copy of the strengthening guide from Dr. Higgins, and he was actually my graduate professor, so he was kind enough to give me some additional support on it and said, let's give it a try. So a lot of the benefits of this is you have your high development strengths, and we have mechanical anchors. You have titanium alloy, which is a ductile material, which means that you don't have the same limitations on how much additional capacity you can add versus an FRP design. And the design process was intuitive, which was nice and easy for me. The guide itself covers a lot. It's a very comprehensive guide. This is the AASHTO publication. You have your material properties, construction tolerances, installation recommendations, design overview, and even some design examples are included. So it's really a comprehensive and easy to use guide. And the methodology, so this is what I really liked, is it was very familiar to me. It looked similar to the AASHTO LRFD bridge design guide. It's using modified compression field theory, which is what we used in the load rating for the bridge. And your steel and titanium stirrups are all assumed to be at the respective yield stress at ultimate. And so you get all that capacity out of all that capacity out of my steel stirrups that were there, but they were there and I wanted to get credit for them. And so that's one of the benefits of having that ductile material. And the way that it works itself into the design process is you just get your normal terms there, right? V sub C, concrete contribution, that's normal, stuff that we're familiar with. V sub S, your mild steel reinforcement, also very normal, right? We know that. V sub TI, your titanium contribution, it looks just like your V sub S contribution, only you have that additional factor in front of it. So it's very familiar from a design standpoint. That additional factor is the environmental exposure factor, and it's relative to the epoxy and the exposure of that epoxy. So it's to account to that environmental degradation that you could have from the resin itself. And it's not a huge penalty, but you have either a 1.0 or a 0.85. I don't want to go into all the equations here for the sake of time. I want to get into the constructability and construction sections of this. Just kind of highlight here that, these do need to be deformed bars. They need to have some level of confidence in their development of it. The guide provides some recommendations on how to account for the reduction in your effective area based on the deformations that you have. The bars that we used came from Perryman Company, and they're a vendor that's here. Should give you all the information you could ever want on this stuff. For me, it just basically looked like a threaded rod. and that you just have to have a little bit of a penalty for reduction in that effective area. Very, very high strengths, right? So you have a grade 130 or a grade 140. You got a 140 or 130 KSI yield strength, right? So for your diameter of bar, you're getting a lot of bang for your buck because you're getting all that yield capacity out of it. And it's a ductile material. The modulus elasticity is 15,000 KSI. So my first design iteration, I wanted to strengthen all of the stems. I had access to just the cells 1 and 3, and so I said, okay, we'll go inside the box. We'll do this installation on the inside. That's the red bars there where they would come in. You could rotor hammer in and develop the ends of the bars that way, and then do a saw cut groove for the near surface mount portion of it. I'm really glad that I followed up on this. So a number 3 bar, and I mentioned the modulus elasticity is a little bit lower. Like this stuff feels like it should be pretty flexible, right? And so in my head, you could drill that lower hole, you could drill the upper hole, you could put the bar in, you could bend it down, and you could push it in, right? It seemed very feasible. I was really, really nervous about that assumption because it was going to be our own bridge crews that were going to go in there and install this. And I showed the picture of the box to start with, and it was not going to be comfortable. You're going to have to install a lot of these. Jill sent me a sample of the number 3 bar, and I went to my cubicle, and I tried really hard to bend it down and up and in into a slot, and realized that, yes, it probably would be possible, but it would be awful. It was definitely not a constructable, construction-friendly detail. And so we went from that and said, okay, we're going to strengthen just the exterior stems. Remember, we're looking at this as a whole width approach. These are box girders, so they're very torsionally stiff. The idea is that you can't just fail an interior stem, you have to fail the entire box. And so it's not necessarily again, it wasn't my first iteration, but it was the one that we went with because now you're working outside the box, you get out of that confined space situation, and the bridge itself isn't, it's not awfully wide. And so we're going to go with the whole width approach, and we're going to just strengthen the exterior stems. From there, went and looked at, what's our required bar size and what's a spacing that we could select to avoid potential conflicts with the existing stirrups, right? I already know I got post-tensioning in there. I got temperature steel and longitudinal mild reinforcing. I want to try and miss as much steel as I can. So we went with an 8-inch spacing so that we could offset it from the 12 or 24-inch and not end up lining up on top of it, and went through the calcs and came up with additional titanium we needed. And so we ended up with a number 5 bar. So bigger than that number 3, but certainly not unheard of size, very common. Within the guide spec, you have a lot of different checks that you have on your maximum spacings. Again, very, very similar equations that you'll be familiar with from doing mild reinforcing design, and came out that my 8 inches is going to be okay. You have a minimum transverse reinforcement. And again, I'm just showing these calculations to show that they're there, that they're familiar, and that they're just another check you're going to do with doing this titanium design. The guide spec shows some standard detailing for doing a typical RCDG shear strengthening. And these are great details. If I could use these details, I would have. For my post-tension box girder, I had to do some modifications because of the limitations. And so it was flexible on that. One of the things that's really good about these details, you have those 90-degree hooked ends. You develop that mechanical anchorage, so you get that, you get your capacity developed quickly. The titanium bars are quite flexible, and so on that image on sketch A, you put the hook in at one side and you just bend the stirrup around the girder and then put the hook in on the other side. And so it's fairly flexible, and that's easy enough to construct. There's another double leg option there where you do an additional hook, so they're just on one side. For our box, these are the strengthening limits that we were looking at. And this is an example of what it would be like when you overlay that 8-inch spacing on top of the 12-inch and then carrying it through to the 24-inch so you get out of those high shear regions. We go from having hardly any steel in there to having lots of, steel and titanium. Getting back into that design. So I could do the 90-degree hook at the bottom. That one I felt pretty good about. Up at the top, I had some additional complications. And so kind of blow up that detail A up at the top there. And you can see I have, where I'm at the pier, where's the highest shear area, and that's where all the post-tensioning ducts are diving up, right? That's a negative moment region for this design, where you have that cantilever end span. And so all my post-tensioning ducts are diving up to where I'm trying to anchor that bar, right? That made me nervous. And so instead of doing a 90 at the top and trying to avoid conflicts, we went ahead and dove that bar at, I think it was like a 30-degree angle going up into the deck itself. The sketch on the left, that's what the saw cut groove looks like. There's guidance in the guide spec for the size of groove relative to the size of bar. For number 5 bar, and it'd be in a 1-inch square cut groove with your resin installed around it. Up at the ends of the bar where you have that 90, obviously that's not saw cut, that's a roto hammer. And there's my post-tensioning ducts that we're really trying to mess, right? But I don't have, this was built in the 50s. I don't have shop drawings or any real high-level detail of where all those strands are. I just have the general profile. This spot right here had me really nervous, right? Do no harm. And I'm trying to strengthen the bridge so that it rates out. I am not trying to take out the post-tensioning and actually cause damage to the bridge. So I said, okay, well, we need to do some GPR, right? I need to have a little bit better idea. I got my design that has a very tight tolerance. Nobody builds stuff the way that they're actually shown on the plans, and so you have to accommodate that. Got together a GPR contract. We wanted to mark out the ducts. We wanted to mark out the existing stirrups and just try and avoid our conflicts. I had a really short timeline, right? So I couldn't go out with a proposal or an RFP and get proposals and grade everyone based on their qualifications. I had to go and get 3 bids, and the low bid won. I'll get into that here in a minute, but it was not the way to do this. So here's the GPR unit came out, and for those of you that don't have familiarity with GPR, this is kind of what you get back on your screen. You get that peak of where there's a rebar on this kind of oscilloscope looking thing, and that's where they mark out that there's a rebar. I show this just to show that there's some level of technical skill with the operators that are doing this layout. I am not a GPR expert. I just have learned that there is some skill attached to that. When they were done, this is kind of what our lookout came up with. Blue lines were the stirrups. They added in a few additional there that weren't actually stirrups. Didn't resolve exactly what they were marking on that. Just some errors. And then the red is the profile, and you can see the profile of the post-tensioning ducts, and you can see how some of those are diving upward. Going up towards the deck in that negative moment region. We also went up to the deck so we could look down and get a good idea of where is the stem walls and where's that duct bundle going up towards the deck. Right, I had assumed that they would stop it at the elevation of that lower reinforcing, so that lower deck reinforcement, but we were trying to get a little bit better handle on exactly what it looked like and where we were at. And then we did a little bit of field verification. So we did a little destructive being out there. You can see the blue line lines up with the stirrup there. We found our post-tensioning duct, verified the diameter of it, patched that back up when we were done. GPR takes a little bit of skill. So all of a sudden I got to one side of the bridge and I saw all these ducts doing this dive up into the deck, and said that's not right. After we had a little bit of conversation, discussed kind of what we were looking for and how it should go, we got that corrected and said that that's not where it should be. But just kind of a word of caution that you want to follow up with some logic. Does this make sense what I'm seeing from the layout? Layout our cutting grooves here. We consulted out the saw cutting work and actually the drilling work as well. I mean, this worked really slick. So because we had everything laid out, they were able to install some small anchors, set up their track and do the wet saw cut. They have their containment set up, and this really went pretty quick. They did good work, except for that top anchor. So that top anchor I was really worried about, right? Like there was not a lot of wiggle room to where you just start hitting ducks at the top. And so when I asked how you're going to drill that hole, they said, well, we're going to hold it about like this. And I said, whoa, that makes me nervous. Let me work with our bridge crews. And so I worked with the bridge crews, and we came up with this kind of channel with a pipe that was set at the right angle so that they could just hold it up into place and then drill it. And with that, we didn't have any conflicts with that upper hole. So that worked out real slick. Construction tolerances are important to consider when you're doing this work. The anchor holes are typically only 1/8 inch larger than the bar size. So if you had that standard kind of 90 degrees on each side, you don't have a lot of tolerance for your holes to be in the wrong spot and your titanium rods to still go in and and still fit. So the location of the anchor holes and the bar hooks need to be precise or it won't fit correctly. So it's probably more precise than your standard specification covers for just drilling concrete, right? So think about that when you're writing your plans, if you're going to bid this work or if you're working with your own crews on how you're going to do it. Conflicts with existing reinforcement can always cause trouble during installation. If you're drilling into concrete, you should plan on hitting some steel. I mean, at least that's been my experience. I can't recall having that where everything was built just per plan and I missed everything. Like I always hit something and you get that phone call. For our application, we had a pretty consistent layout, but we still wanted to make sure we were going to be okay as the titanium bars were on their way. And so what we did is we had the supplier do the 90-degree bend at the bottom for us, and then make the bars 3 inches longer, and then said we'll do the other bend ourselves, and then we'll have a little bit of room, that extra 3 inches, to where we could trim them up. So that's what we did. Did all of our layout, drilled all of our holes, did our saw cutting, and then field measured where it went. It wasn't that bad. Like I said, we were pretty consistent. So it was like the crew did 80% of the bars on the standard and fit those in wherever they fit, and then went back through and field measured and adjusted as they had to. Bending the bars is, it's really pretty straightforward. It's very similar to bending your mild reinforcing. The only trick is you got to heat it. And heating it's actually really pretty easy. It turns blue when it's at the right temperature. So you torch it till it turns blue with your propane or oxygen torch. Hits that 1200 degrees. Go ahead and make your bend, and you're off and running. This is the installation process. So you want to fill up the grooves about 2/3, 3/4 full of the epoxy to start with. And that way when the bar goes in, it squishes it out. Here they are feeding in that top 30-degree angle up towards the end of the deck. You can see the little kind of circles on it, or washers. Those are just a spacer to help make sure the bar stays centered in the hole once it goes in. And here it is as that epoxy squishes out from around and behind the bar. Fill up the top if you have any extra, and then strike it clean. I thought it looked pretty cool. It was like a pink tiger stripe when it was all said and done. If that's not the look you're going for, you could always do like a little skim coat over the top or paint it. I think we left it because, like I said, I like people to know that maintenance was here. A timeline. We didn't meet the current 30-day load posting requirement, but fortunately we had a little bit of flexibility back then, and so our load rating was finalized in December, and for June we had all the construction work complete. We did have a couple snowstorms in the middle, which is really uncommon for this area, and that just shuts down the entire state. So nobody was driving over the bridge for a few weeks of that timeline. And then cost. Everyone wants to know about cost, right? Titanium bars. This is crazy. You can't use titanium bars in bridge. Secondly, bridge maintenance. So the total project cost was $167,000. Again, this was done in-house with in-house design, in-house maintenance, and so we kept the labor costs fairly low. Let's jump to the bottom bullet here real quick. Out of that $167,000, $19,000 was the cost of the epoxy, and $17,000 was the cost of the titanium. And it ended up only being 10% of the total project costs. So there's something to kind of consider on when you're looking at different materials. The high strength of the titanium allowed us to use fewer bars, which would help keep our labor costs down. And so what we found on this project, and actually we've done quite a few in Oregon through maintenance for different reasons, that titanium ended up being a very viable, cost-effective option. Lessons learned. Do not assume the structure was built per plan. Verify design is constructible before finalizing it. GPR is not a good candidate for low bid, at least not in this application. I will never do that again. Even with good NDE investigation, you will hit some rebar. Have it in your head to know what you're going to tell the crew or the contractor when they hit it, right? What bars do you need to miss and what bars can you live without? And then again, cost isn't a huge factor there. Your labor, traffic control are the big drivers for these kind of projects. So my contact information there, feel free to reach out if you have anything for me. There is going to be another presentation on titanium from Dr. Higgins here in just a minute. So any questions? Have I personally done any more since then? I have not. Oregon has. There have been quite a few strengthenings for flexure. We also had some where it was actually the very first application was when back in the 50s they were being really cheap with the reinforcing seal and they stopped the bar as quick as they could. And we had some where we actually had that longitudinal tension check, failed that check, and we actually had the big crack developing in the bridge at that termination point, and we used the titanium to tie the bridge back together. That was a cool one.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.